Hello everyone, and now we are going to create matrices or vectors within MATLAB and learning how to do that. You might have already seen me do it a couple of times, but let me explicitly state exactly how you do this. So the first thing that you need to do for a normal vector, you just say A, or your name of your vector. I'll call this vector. Is going to equal to, if I take one value, it's a scalar. However, I can use my brackets. If you see, these are called brackets, the square brackets in particular. We'll say, okay, MATLAB, I am now creating a matrix or a vector. So it's now going to be a group of numbers. So all I have to do is create a group of numbers with commas in between them. As one example, hit enter, and I'll create a vector called that. Alternatively, I can go back in and just simply put spaces and hit enter, and I get the exact same vector. So this will create in a row your vector, right? In a single row, it's created that, and you can explicitly, and this allows you to create independent numbers in every position, however you want, one by one by one by one, to create your vector. The next thing you can do, though, and this is only good for rows, the next way you can get around this, let's say you wanted to create a column vector. Well, rather than commas to separate them, we can go back in and put semicolons. Remember, semicolons suppresses at the end of a column, at the end of a function, the presentation of it. But inside the brackets of a array defining feature, inside the square brackets, it tells the computer, oh, new line, new line, new line, and it creates a column vector. Excellent, very good. So now all you have to do is put these two elements together to create your array. So if I'm going to say CLC, and I say my array now is going to equal to brackets, I can say 1, 2, 3, and then I can put a semicolon and say 4, 5, 6, and I can put a semicolon, 7, 8, 9, put a end brackets, and I get a 2D array. That is by far and away the really nice way of getting a range of numbers or an array of numbers very nicely. Now you'll notice here, this is a little bit cumbersome because it's kind of hard to enter in all those arrays and numbers, and it might not be the easiest way to visualize it. So alternatively, if you use the Shift Enter key, so I'm gonna delete this. Oh, I'm doing things horrible, so I'm just going to delete all these lines. If I was to say array is equal to 4, 2, 1, and now rather than hit semicolon, I can put a semicolon there. I'll put that in there just for the sake of it. If I hit Shift Enter, you'll notice it doesn't actually enter into the line. Holding down the Shift key and then hitting Enter causes the cursor to go to the next line, but it didn't actually enter it in as command yet in the command window. I can tab over, and I'm just doing this for the sake of space, but I can say 10, 2, and 3, and I can Shift Enter again and go 1, 1, 1, end brackets, hit Enter, and you'll notice it's created this very nice array in the same format that I entered it in as. If I was to do this I'll clear this, and this is a very convenient approach, and I'm going to bring this down, this window, so you can see my, oops, oh no, I'm doing horrible things. Okay, here we go. If I bring this up, stop that. Okay, bring this down. And in our M file example, if I have an M file, this is where it gets really convenient because I can say my data is equal to, and I can say 1, 2, 3, 4, 5, hit Enter, 6, 7, 8, 9, 10, however I want to do it. You'll notice in this example here, I didn't put anything else in. I didn't have anything in there. I can just type it in as I would anything else. I just have spaces and so forth. You'll notice right away, very nicely, when I hit Enter, when I hit Enter, let me go back to this. I hit 4, 5, hit Enter. It goes, and I can put spaces in there again, and it'll actually, as it's entering it in, it'll recognize that I'm creating an array, and it'll tab under the previous start point. And this is just a nice convenient utility to keep track of how many positions or otherwise that I have. And if I hit enter, it goes back to where it was. So anyways, if I hit save, bring up the command window, minimize this just so you can see, and I hit run, it's created the data set as we typed it in above. So you can actually enter it in logically how you'd like, as you'd like in this. And this is a very powerful tool within the M code because it keeps things clean and easy to follow and simple. Of course, however, this isn't the most convenient way of entering in numbers. If you have to enter it in one at a time, sometimes that's the only way you can do it, because if you have complex data sets that that you don't want to deal with, well, how do you get around that? Well, there are some shortcuts in defining and creating arrays. One example is simply the colon feature. And colon, of the key things in MATLAB that I think you need to know and be comfortable with, percent is one of them, semicolon is another, colon is the third. What the colon does for us is if we created an array, I could say array, let's say a vector. And this vector, I'm going to make it go from 1 to 10. If I put a colon there, watch what happens. It creates a vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, spaced by ones in there. If you need a little help to see what MATLAB is doing with that, do help colon, and it'll give you much more information than you probably want to know about it. But you can read through this and get a sense of what the colon command does. You can do it outside, you can do it inside. So I can say vector 1 colon 10, and then I could say 2 colon 11. It's the colon without any other information. It's going to space it by 1 every space. And so as long as these are matched and I hit enter, it's creating one row that goes from 1 to 10 and the second row that goes from 2 to 11. Exactly, in just very simple ways, creating this. Thirdly, one additional feature I can do here is, oops, let me go back, is I could actually do a vector. And let's say I don't want to space it by ones. Let's say I want to create a vector that goes from 1 to 5, but I want to space it by 0.1. Well, put a new colon in between the beginning and end and tell the spacing that you want to use. In this case, 0.1. And now you'll see you get this rather large, and it's breaks it up. And this is a little weird way to see it, but you'll notice column 1 through 8 is telling you is this one. Column 9 through 16 is telling you this one. And so it breaks it up into these columns very cleanly, very nicely, and you can get a sense of what the size is. You can look over here and you can see, oh, it's got 41 positions that we just created for all the variables 1 to 10, and all the ones in between comes out to be 41 numbers. Is how it's spaced. Perhaps I don't want this as a column vector. Maybe I want it as a row vector. Maybe I want it as a column vector. In which case, I can say vector is equal to vector, and I put an apostrophe. The apostrophe will be the transpose feature, and it's going to transpose it from in the number, and now we get a nice column vector of the numbers that we had just created. So that's a very useful feature as well. Other shortcuts exist. The line space and log space. I'm not going to enter these in just yet, but those are two other shortcuts that you can use. Line space is nice because if we type that in, I'll do help line space, and then you'll see here it creates a linearly spaced vector, generates a row vector of 100 linearly equally spaced if you don't tell the number of spacings you want. However, let's say you want a spacing from 1 to 10, and you want them to all be evenly spaced within there by a certain number. Line space will do that. So if I created, I don't know, vector Tom, and I want me to be spaced lin space between -5 and 5, and what do you see here? The other nice thing about MATLAB, it'll often pop up with help as you go through in case you need help. So check that out. And then the number of spacings you want. I want 10,000 numbers. I'm not displaying those. And you get a nice 10,000 double position on there. I don't have to do anything else. I don't actually have to know what the spacing is on that. But we can go in and check that out. by referring to the elements within a space that exists. So let's if I wanted to know what the second space is in that array, I can actually call within the vector a single element through parentheses. So for example, if I said parentheses 1, I'll get the very first element in that array, -5, which is good. If I said, because we know 10,000 is the final number, 10, 1, 2, 3, and this is the index, this is called an index value. I hit enter, it gives me 5, it's the final position. What if I said Tom2, it's -0.4999, which obviously had to be the spacing for 10,000 in this. The final interesting part here is if I said Tom 1, 2, if I said Tom 20,000, what happens? Index exceeds dimensions. You might remember this from when we had the sign function error, because the position here, when I put parentheses on an array, it's actually asking for the number at that position in the array. And since I asked for an index that's larger than the size of the number of indices here, this is the error we get. So that's a nice thing to see. Log, jump cut, sorry. So log space is similar to linspace, but you can imagine it's just going to space it based on the log positioning. So if I was to say b log space here, the first number will be the 10 to the power of 1 to, say, 10 to the power of 5, and the number of spaces we want. Let's say if we said 5 spaces, then we'll get 10, 100, 1000, and so forth. If we said it was 10 spaces, it would do the same positioning from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to that position. Now, what do you notice here? And this is an important point, and one of the reasons why I wanted to show this. In this one, the number is presented in a very clean format: 10, 100, 1000, 10,000, 100,000. That looks all nice. But what did MATLAB do in this case? It does what it calls a common scaling factor. When you start to have numbers that vary largely, or the numbers get very big, and it can't be presented in the normal format that it's used to, it will create a multiple in the beginning that's multiplying all these other values to, assuming that's what the final value is. So this first position here is 0.0001 times 10 to the 5th power, and so forth. So remember, this is a common scaling factor for the entire columns, and be very careful of that, because oftentimes you don't want to necessarily report the answer without this if that's not the way you want to look at it. And so be aware of that. Let's see, I'll see it clear. Now, one other point to note with the spacing, with the colon feature, I'm not limited to just using simple numbers in that. So I don't have to just say 1 to, in increments of 5 to 500. I can actually put calculations in here. So let's say, for example, I wanted to create an array of numbers from 0 to 2 pi, and I wanted that 0 to 2 pi to be increments of, say, spaced evenly by pi over 10. I can do that. I can say 0, space it by pi over 10, and take it to 2 pi. And then I'll get numbers spaced appropriately as that. Why do we like that? Well, now that I have that angle, I can create a y is equal to sine of that angle. And then if I plot, and we'll talk more about plotting later, but if I said plot of angle versus y, you should get a really nice plot, evenly spaced on this vector position that we have. You notice there's still angles here. It might be kind of hard to see because they are not perfect. We don't have enough data points to make it a smooth curve, but that just gives you a sense of how you can actually use these shortcuts to your advantage and make things a lot simpler. Now finally, and the very last part of this, and why we like arrays so much, is because we can do calculations together in concert with each other. So what do I mean by that? Well, if, for example, I said an array was equal to b is equal to 4, 5, and 6, and I wanted to add 5 to all those. All I'd have to say is b plus 5. And you'll notice 5 is added to each one of those numbers. That's nice. So I'm going to clear that screen. I'm going to bring b back up. But let's say a is equal to 1, 2, 3. Now, if I wanted to add these two together, all I'd have to do is say a plus b. Note, it's just straight plus. Just straight plus, a plus b. What's going to happen is it's going to take every position, every one in the first position, add it to the one in the next position, and give that the value. So 1 plus 4 is 5. 2 plus 5 is 7. 3 plus 6, 9. So a plus b, you've done a set of complicated calculations together in just one command. This is really where MATLAB begins to shine, because oftentimes we want to do these large crunchy numbers on big data sets, and in Excel you'd have to copy all those in a row, you'd have to make the first cell, you'd have to open that cell across, you'd have to say Control D or copy paste and get that function to go across and do that. Here it's just a matter of 2-3 lines, and those 2-3 lines are entered in the exact same way, whether or not the vector is 1,000,000 positions or 1. That is really where we're going to go from this. Note, this is how we want to keep arrays. The commands in arrays are plus, minus for the positions. And you notice it's the same thing for plus or minus in matrices as well. Or for multiplication, it's dot star. For division, it's dot divide. Or for power, it is dot to the power. And my general rule of thumb is if you're doing something, when in doubt, put a dot in there. You almost, unless you're doing a matrix calculation for actual doing matrix algebra, you're almost never going to make a mistake if you put a dot. So as long as it's if it's a star, slash, or caret, always do the dots almost. So I can't think of examples where that would fail you. So just to give you an example of how this works, a, b, and if I said a dot times b, you can see again it's 4, 5 times 2 is 10, 6 times 3, 18. If I said a dot divide b, you see that behavior. It's 1 divided by 4 is 0.2, 2 divided by 5 is 0.4, and 3 divided by 6 is 0.5. And if I said a dot to the power of b, it's obviously 1 to the power of 4, 1, 2 to the power of 5, 32, 3 to the power of 6, 729. And that's it. That's really the crux of the entire biscuit here. This is what the calculations you can have in MATLAB. Now, I began discussing a little bit about indexing in MATLAB in vectors. There's a lot more that's involved in there, and we'll save that for the next several videos. So thanks a lot, and goodbye.